Hi everyone, welcome to this tutorial session of this Big 10. So today we are going to discuss about the radiation, uh, how it can be, how it is emitted from electromagnetic, how in previous week we have seen how this electromagnetic wave equation comes from this Maxwell equation. Now with this week we will see so how this electromagnetic radiation is generated, like what is the origin of this electromagnetic radiation. And so with this, but because there are very few people now, so I will wait for I think 3-4 minutes, then we will start. And in the meantime, what I will do, so I so all these sessions will be recorded and they will be uploaded on YouTube. So here you can watch them later on based on your convenience, and you can ask the questions in Google Forum where the your questions and queries will be uh, solved. And also the presentations and uh, other things that are used in the video will be shared with you. And so uh, like the other weeks, this week also, uh, we will record this session and upload it on YouTube. I think I will wait for 1 or 2 more minutes. Okay, so I think we can start now. So as I discussed earlier, like we will today we will see how we are going to get the source of electromagnetic radiation, like what it is that gives rise to the generation of electromagnetic spectrum. Means like in last time we have seen that using, okay, so recall this Maxwell's equation. So here you can see that's the complete Maxwell equation. There is the source terms are present like rho and the current density J. So this is del dot E is equal to 1 over epsilon naught rho, that is due to Gauss law of electrodynamics, and then del dot B is equal to 0. So it has no name, and del cross E is equal to minus del B over del T. That's Faraday's law. So this is changing magnetic field generates an electric field, and then you have this del cross B is equal to mu 0 J plus mu 0 epsilon naught del E over del T, where changing electric field generates a magnetic field. Now, if you can recall that using Maxwell's source free equation, so we have written down the theory for sorry, we have derived the equation for wave equation for this electromagnetic uh, waves. So in that time, we omitted the rho term and the J0 term. So what happens when we don't omit these terms? So what will become of that wave equation? So first, let us recall very quickly like how we have derived the Maxwell's equation using rho zero and J zero approximation. Not approximation, like there is no charges or there is no charge current. So it's a source-free Maxwell equation. So we have found if okay. So let us see what happens. So I will share my screen. Okay. Now I will share my screen. So I hope you can see my screen. So uh, we have seen that previous cases del where we have this source free Maxwell equation that we can write as the first one was del dot E is equal to 0 because we have rho is equal to 0. The second one was no name, the Gauss law, but this one has no name. And it says that the magnetic field does not have any charges, any magnetic charges, and that means whatever is going through some surface is coming back to that. It's closed field, or it has closed field lines. So it has this, and then the third one is del cross E is equal to minus del B over del T. This was the Faraday's law, and the fourth one is and the fourth one is del cross B is equal to mu 0 J plus mu 0 epsilon 0 del E over del T. Since it's the source free, means there is J also 0. So this terms goes away, and this is the source free Maxwell's Maxwell's equations, where we have where we have rho is equal to 0, comma, J is equal to 0. Means the charge current density. So rho is this charge current density, and J is, sorry, this is charge density, not current. Charge density, and this is the charge current density. Now using this, we have derived, recall. So we had this del dot, recall we have derived this wave equation using the above four equations. So these are the four equations that we have used. One, equation. Now I'm going to just quickly show you how you can do that. So the equation three, equation three is equation three is given as del dot E is equal to minus del B over del T, sorry, del times E. Now you take another curl of this, so you will have minus del B over del T, del cross B. And now what will happen is that del cross uh, del cross E can be written as del vector del dot del dot E, and minus del cross square, so del square, and E vector is equal to minus del T del cross B. But now what happens that we know from equation 4 is that del cross B in the case of source free is mu 0 epsilon 0 del E over del T, and that gives rise to this. If we substitute the value here, so we will have del, but the del dot is also 0 from equation 1. If this term is 0, we have minus del square E vector is equal to minus del over del T. Del cross B is nothing but mu 0 epsilon 0 del E over del T, and that means we have minus del square E is equal to minus mu 0 epsilon 0 del square E over del T square, and that means we can write this as del square E, sorry, del square E vector minus mu 0 epsilon 0 del square E over del T square equal to 0. And this is nothing but with we know the value that C is under root 0 epsilon 0. That means mu 0 epsilon 0 will be 1 over C square. Let's substitute that. So del square E minus 1 over C square del square E over del T square is equal to 0. That means this is what? This is electromagnetic equation. So this was earlier we have seen. Now what we have to now what we are going to do now is to see to derive the electromagnetic wave equation presence of source. So we have recall that source, the Maxwell's equation with sources. del dot E is equal to rho over epsilon naught. This is equation 1. The equation 2 is del dot B is equal to 0. Then equation 3 is del cross E is equal to minus del B over del T. And the equation 4 is del cross B is equal to mu 0 J plus mu 0 epsilon 0 del E over del T. Okay. This is all that we have. So what we can do, which, we can just do the same thing. We can take the curl of the equation 3. The motivation is that if we take the curl of this side, so del cross will be here, and then we will know the value of del cross B. So this is what the motivation is. We can write this as here. Then we have minus del B. So it become del cross B over del T. Now you already know that this is going to be dot del dot E minus del square E, and you have already this, so it's a minus del over del T of mu 0 J plus mu 0 epsilon 0 del square del E vector over del T. Now you know that this is nothing but del dot of rho over epsilon naught, and then you have del square E equal to minus del over del T. Del over del T is mu 0 J, and mu 0 J minus mu 0 epsilon 0 del square E over del T square, and that means we have this del square E plus mu 0 epsilon 0 del square E over del T square, and this is the minus, and here we have minus del over del T 0 J and del dot rho over epsilon naught. So that now what we can understand from here, that this is nothing but del square E, and this mu 0 is 1 over c square del square E over del T square is equal to minus minus plus del over del T mu 0 J minus del of over epsilon naught. So you can see that uh, what is giving rise to this wave equation, means this electromagnetic radiation, it are the terms here and here. And what is happening, that the current itself is changing with the time, and the electron and this charge density, it's a function of this. We are taking the gradient. That means it will change with the space. Means that in space at any point, it's not the same. There is some charge gradient. So that means if there is a charge gradient and the electromagnetic field and also the charge current is changing with respect to time, so then there is going to be a generation of electromagnetic radiation that is given by the equation in the left. So now the next is now we will go to our questions. Like, so I want to make you understand first that if you see here, so what gives rise to the electromagnetic fields? So what is giving rise to electromagnetic field is the radiation that uh, that is generated by the some kind of change of charge current density, charge current density or the uh, charge density itself. So because in the right hand side we have seen that sorry, it gives rise to the it gives rise to the electromagnetic wave equation where the right hand side is the source term that are sent to uh, for such for such uh, electromagnetic wave equations. Okay, so uh, I think this has the minus sign. So if I have made a mistake, please correct that. So this comes with the minus sign. So here, when I have written this, I have del dot E is equal to minus rho upon epsilon naught. Okay, no, this does not come with a minus sign. It comes in the when voltage is there. Means the potential in terms of potential it comes, but not with this. But whatever the case, del dot E should be here as this thing, and when we do this, this will become positive, and this should become like this. So I think there is this confusion that this should have a minus sign, and once we multiply this with the minus sign, it becomes positive. So, but we can see that this is the source term. Oh, I'm not sharing my screen too much. This thing I have written by mistake, wrong thing. This should be a plus sign on the right hand side on this charge density. Okay. Now what we can do with this, what we can understand. So we can see immediately. Uh, okay, so with this, we can see that there are two things. This is okay. Let me write. This is one. This is two. The first one is del dot t is equal to mu zero j. So this is the changing current time. Will give you electromagnetic radiation. Second one is that del dot del rho sorry epsilon naught is also the source term. So what will happen? The spatial change time, the spatial change, uh, the charge current density will electric. Sorry for a moment. charge current and the changing in the charge current with time, or changing in the spatial charge current density will give you the electric field. Okay. So, and what happens to magnetic field? So we know that there is this del cross B is equal to mu 0 J plus mu 0 epsilon 0 del E over del T. So what we can do about this? Let's see. So del cross, we take the cross both side, then we will have del cross times del cross B, and that means it will have mu 0 del cross J plus mu 0 epsilon 0 del E over del T del cross E. And what does it give us is the following, that del cross B del cross it will become like del of del dot B. Okay, and then again we will have del square B vector is equal to mu 0, and then you have del of del cross, so it's a del cross J plus mu 0 epsilon 0 del over del T, and you know that del cross E is equal to minus del U over del T, right? So del cross E is minus del U over del T. Now what we can do, again, we have system 0, or del dot V is 0. So we will have mu 0 epsilon 0 del over del T del V del square V over del T square, and with a minus sign, and plus del square V is equal to mu 0 minus del cross G. Okay. Now this can be written as del square V minus mu 0 epsilon 0 del square V over del T square equal to minus mu 0 del cross G. So here you can see that del cross J is the source for generating this magnetic field component of electromagnetic radiation. So this is the source for generating the magnetic magnetic field from electromagnetic. Now what? Oh, okay. So with this, we can see this very easily, like how in real world how this can be understood. So this was all the mathematical description, but let us see an example where we can easily see how this electromagnetic waves are generated. So I will resume presenting. Here you can see. So just like so let us consider a simple scenario that you can understand by just looking at it. So let's say you have a string that is like this, that is straight like this, and then you start to oscillate this point. So this point will go up or down. So based on the string, like it will you have some amplitude in y direction that you are oscillating with. That oscillations will travel towards x, and the and the displacement at any point x with time can be given as y is equal to a sine omega t minus kx. So sine omega t minus kx just shows you that it's a traveling wave equation, and it is a plane wave solution, but it shows that the disturbance caused by this force here, like whatever we are oscillating here, it being traveled to this point, this at this end, okay, somehow, and that so in the same way, if we have a charged sheet with sigma charged surface charge density, if we are moving it with the velocity v in the direction of x, so what will happen that there will be an induced magnetic induced electric field that is given by this sigma naught 0 x cap, and then it will generate an magnetic field, and perpendicular to both there will be an propagating s vector that you can see. So here you can see that this goes to this side, and this is the whole propagating vector that you can you can understand just by looking at it, that the propagating vector x, the magnetic field generated induced by this changing uh, electric field, and the electric field itself changing with space, you because the charge density that is there at any given point, let's say you consider some square, okay, some square type of surface. So what happens if you move that is if you move this sigma, this is charge plate. So in that square, that whatever you consider the Gaussian surface, the charge density will change spatially, because before that it was uniform, but after it moving, let's say half the part of that Gaussian surface is covered, half it not. So what will happen that the charge that there will be a special charge gradient, and that will generate an electric field, and that electric field is changing because you are moving up and down, so it will also generate a magnetic field, and that magnetic field will generate, so these electric and magnetic field will propagate along this perpendicular direction, which is perpendicular to both E and B. So red one is B, blue one is E, and the propagation vector is in the black one. So here you can also see, notice one thing, that E and B are perpendicular to the propagation direction, and they are mutually perpendicular also. So if we calculate the E dot B, it will be 0. And here you can see that how this wave propagates. So it's propagating along Y, but the oscillation of the electric field and the magnetic field are in Z and the X direction. So E cross B, so X cross Z, uh, sorry, Z cross X is Y cap. So you can see that it's traveling along the Y cap direction, which is perpendicular to both X and G cap. And one thing you can also notice, since it's a sine wave, so it has two trough and two uh, like two higher points, and okay, so you know the trough and the distance between the trough gives you this lambda, and you can also calculate between, it's a relative thing, so you can also calculate between two maximas or minimas. So if you add two maximas, let's say here and here, so it's a lambda, it's, and always constant. So that means that it's traveling with a uniform velocity. Okay. So here you can see that electromagnetic wave direction is perpendicular to both x and z direction. Okay. So derive the wave equation from the Maxwell's equation in presence of source. So we have done that. We have just seen that in the presence of source term, the Maxwell's wave equation. So whatever that comes from the Maxwell's equation gets modified, and it's not just a plain wave solution, because there is this source term. So in presence of source term, how which type of solutions will be there? But then it is also clear from that there also that source terms are the reason to generate this kind of electromagnetic wave. Question two is the entire theory of electromagnetic waves is contained in Maxwell's equation. So we have just seen that yes, it's the entire theory of Maxwell's equation, electromagnetic waves is contained in the Maxwell's equation. That's true because we can have we can write down the Maxwell's equation in the media, means in the media, and then we can calculate how much electromagnetic wave will travel inside the media, or we can describe the light coming from the sun to earth using Maxwell's equation, because uh, because light is an electromagnetic radiation and it does not need any medium, and then there is vacuum between earth and the sun. Even though the radiation from the sun comes to earth, that that is described by the Maxwell's equation, because the Maxwell's equation shows that in the vacuum light travels with the speed c, and it does not need any medium to propagate. And that's how we can understand this, that yes, entire theory of electromagnetic waves is contained in Maxwell equation. Third one is the magnetic field can be produced by conduction current, displacement current, both conduction current, both. So question number three is magnetic field can be produced by conduction current, displacement current, both conduction and displacement current. It is produced naturally. So what does it mean? We have just seen the this Maxwell's Maxwell's equation. So let me show you once again. So what we have actually this thing. So here it has del times b arch mu 0 j well mu 0 epsilon 0 del e over del t. Sorry. So the question is asked is the asked question is magnetic field can be produced by conduction current, displacement current, both conduction and displacement current. It's produced naturally. So what we can say is that first of all, you can see here these two terms, and this is the magnetic field. So this one is called uh, conduction current, conduction current, and the other one is this one is has this electric field, but this is called displacement current. But you might be wondering, oh, where is the displacement in this current, and where is the current actually? So it's like this: the JD current, JD displacement is defined as epsilon 0 del E over vector T. So if you rewrite this equation, you can write del cross B is equal to mu 0 J C, or charge current or conduction current, plus mu 0 epsilon 0 del E over del T, and sorry, so epsilon 0 and del E over del T JD. So you can write this as like this. So del cross B is equal to mu 0 JC plus JD. So we can see that the magnetic field not only not only depends on the electric field, but also it depends on the charge current. So uh, it, but the dependence of the electric field, but the dependence dependence on the electric field is re rewritten as JD equal to epsilon naught del E over del T. So, it shows that the conduction current charge current is the is the conduction current and the displacement current. Sorry, it's rise to the okay. And then again, our next question is so the option that will be corrected by both conduction current and the displacement current. The conduction current, because the electrons that are conducting are generally situated in the conduction band of any metal, so that's why they are called conduction current. Yeah, it does not necessarily mean that it's not a charge current, so they are the same thing. But the charges that are being carried are by the conduction electrons. That's why it's called conduction current. So nothing kind of new. Then we have this question number 4. So which of the following laws do not form a Maxwell equation? Planck's law, Gauss law, Ampere's law. So I think this question can be answered very easily. So let me write it down. The first one is the Ampere's, so Maxwell's equation. Maxwell's equation. First one is del dot E is equal to rho over epsilon naught. Second one is that del dot B is equal to 0. Third one is del cross B is del cross E is equal to minus del B over del T. Fourth one is fourth one is del cross E is equal to minus del. Okay, so it's mu 0 J plus mu 0 R 0 del J over del T. Okay, now what does this mean actually? So what these equations come from? Where do these equations come from? It it so this equation one. Let's say we are talking about the equation one. That is del dot E is equal to rho upon epsilon naught. So if you, this is the differential form of Gauss law. So what was the Gauss law? So Gauss was law was if you have any Gaussian surface and it encloses some charge Q or charge density. So what will happen? That this electric flux that is passing through will be equal to the so it will be equal to the so the flux that is equal to the Q over epsilon naught. But we knew that the flux they were saying what the flux is. Flux was del divergence of E. Sorry, so it was E dot dA. Okay, so what they were calculating at, they were calculating through a surface. Let's say this. Okay, so they were calculating at in a volume at a surface. So what they did, so they were essentially calculating this E dot dA. So they were saying that what how much charges this include uh, this encloses will it will be equal to this enclosed charge. So Q, sorry, this will be Q enclosed over epsilon naught. So this was the enclosed charge. So it's say in the volume, it has and it has some it had some it obviously it had some density, and then the dV will be you will integrate it out, it will give you the Q and upon epsilon naught. But the left hand side is this closed integral. So it was E dot dA. Now what you can say, right, that closed integral of E dot dA is equal to del dot E, volume integral of this whole thing. So this can be written as del dot E dB is equal to over epsilon naught del B dB. And then from here you can compare that this both for an arbitrary volume. It's this, so del dot E is equal to over epsilon. So you can see that from this understanding that this enclosed enclosed flux is equal to the charges enclosed by that surface. Okay, so this is how you can write this. So now what we can do more is we can actually calculate uh, that this comes to the Gauss law. Then the second one is the second one was Faraday's law. So Faraday's law was that EMF, induced EMF, is equal to minus del phi over del t, where phi was the flux change, that was p dot e. So from here, you have this uh, del p over del t into dot dA equal to EMF induced. So EMF is nothing the gradient of E, the circuit, negative sign. So that's why we have this del dot E equal to minus del P over del T. So that because P is nothing but del dot E, that's why we can write this. Okay, so this is this. So okay, but uh, but the okay, so this was like this. This was B dot dA. In general, what will happen? In general, what will happen if you calculate? So, no, I've written it wrong. So, what is this? This voltage, okay. Each del dot to V E dot dl. This is the this. So, this is the E dot dl. E dot dl. And now, when we try to integrate it out over the closed closed like area. So that this area that it been closed, it has some periphery. So at that periphery, we are integrating it out. So you can also integrate it, but this thing, so it can be written as del cross E dot dA. So you don't need to take care of this periphery, you just need to take care of the area element dA. So this can be written like this, and this is minus del T dot dA. And now what you can have del cross E, because for an arbitrary area element, so dA not equal to 0. That means for an arbitrary area element, we have this del cross D equal to minus del P over del T. So what is this? This is nothing but Faraday's law. And the next that is remaining is the third one. Third one is this del cross E, del cross P is equal to. So let's go for okay. Let's say we are talking about in terms of like static electrodynamics, where the charge current and the rho are not changing with the space or time. So we can have this equation, fourth equation. So what we can do, we can see that we know that from Ampere's law, mu I enclosed, and this is nothing but the closed integral of v dot dl. If so, they are saying that is is a wire that is carrying a charge current. Take a closed tube around it and calculate the v dot dl. So what will happen? So this is the magnetic field is v, and this is the dl. So dl is the length here, here, and here, and here, all the here. So you can the generated magnetic field, that is v, will be equal to the mu I enclosed. So the magnetic permeability and the I enclosed is the how much current it includes, this loop includes. Okay, so that means if you write in terms of current density, so you can write this J into dA over. Okay, so this is the current density that is being enclosed in this area element to mu, but the B dot dl is on the surface. It can be written as del cross B dot dA for the area element A. So now if for an arbitrary dA that is not equal to 0, you can see from both sides that del cross B is equal to mu 0 G. That means that this is the Ampere's law, differential form, Ampere's law in differential form. Now what we have left is that what is the first option? The first option is the Planck's law. So Planck's law is not this. Planck's law is for electromagnetic. It's for a cavity. It's a for electromagnetic radiation that is being emitted by a cavity. So that is something different. So we can see, and then there is one more equation that is del. The fourth one is del dot V is equal to 0. But we know that since it's to do solenoidal nature of magnetic field. Okay, so due to that, that means all these things are, yes, can be described by the Maxwell's equation. So it's not the Planck's law is not the form of this Maxwell equation. And then our next question is what is the fundamental origin of electromagnetic radiation? So fundamentally, what happens? We just talked about it that if you see the electromagnetic wave equation, so it's like here. So here, if you see this part, this is the charge, and this part, this is correct. One has to change the with the time, another has to change the charge current gradient with the time. Now the question that is being asked is what is the fundamental origin of electromagnetic radiation? The first option is movement of atomic nuclei. Second is oscillation of electric charges. Third one is the chemical reactions. Fourth one is the gravitational interactions. Now, if you think about it, the movement of atomic nuclei gives what? So it is so if any kind of static motion is going on, so whatever the nuclei is doing, so if it's static, it won't give you anything. So what happens is when the oscillating electric charges. So what happens? The oscillating electric charges, that means that it's going up and down, up and down. So for any given area, the flux is changing. This thing is changing, right? So this change will give you the electromagnetic radiation because del dot rho over epsilon naught for in given volume will change with the time, with change with the space, and this will give you the electromagnetic radiation. And the third is of chemical reactions. No chemical reaction want to give you the radiation, the gravitational interaction that because they are not the charged part. Only charge rho and the changing current J can give you this electromagnetic radiation. Other forces or other quantities won't give you the electromagnetic radiation. So our next question is electromagnetic waves are produced when which of the following occurs? So our next question is electromagnetic waves are produced when which of the following occurs? A magnetic field remains constant, electric charge is stationary, and electric charge accelerates, a neutron decay. So neutron decay has this charge conservation, so it does not contribute to that. But we can eliminate the equation a magnetic field remains constant. So if the magnetic field remains constant, that means that del cross E will be minus del P del T like this. But we know that del B over del T with time should not change. That means the derivative will be zero. This means that del cross E will be zero. But recall, you are taking the del cross E for minus del cross T. So this was the case, but so this thing is, but this thing is zero. So the right hand side is zero. So whatever we were doing, so like because that that del cross B, if you take out the spatial part, but the time part is still zero. So this won't give you any any wave equation, right? Because you have this equation, now you can solve it. So this del cross E equal to zero is the equation that you have, and if you want to solve it, you can check it easily, but it won't give you any wave kind of equation like this del square E minus 1 over c square del square E square over del t square equal to 0. No, the only equation you have is this del square E is equal to 0 because the del B over del T is 0. So in the case of non-changing static magnetic field, we won't get anything. And electric charge is stationary. Okay, so electric charge is stationary. That means it is like Q is here, and you have drawn some surface around. So if it is stationary, so the flux is phi is equal to this radiation, this area A. So this line is coming out from here like this, right? Now what we have to do, we have to check whether this charge okay in this given area whether this phi is changing or not. St phi with the space delta phi changing or not. So we can see that the q is stationary. That means that there is no change in the flux, and that means there won't be any del dots rho type thing, and so this one soon won't generate an electric field or electromagnetic radiation. And then you have the next stage, electric charge accelerates. So yes, that when the electric charge accelerates, so it is changing with the space as well as it's also changing with the its acceleration means that the whatever you have, it is changing with the time. That means the current is itself changing with the time, and also the charge density for any given region is also changing with the time, because sometimes charge will be here and then will move. So at the given time, this will have the zero charge density, but at t equal to zero, it have some finite charge density. But then the difference is that it's changing, and the change in the space in the charge density will give you the electric field that we have seen. And neutron decay, I just told you that the neutron decay is not related to the direction. But because like it's just a simple decay of an particle, accelerating charges will give you the electromagnetic radiation. Then yeah, next question is the relationship between electric field and electromagnetic field in electromagnetic radiation is such that they are parallel to each other, they are perpendicular to each other. So let us write this down. So let's say if you have an electric, so as I told you in the graph, so you have an electromagnetic field. First, let us make the coordinate system. So we have this x, y, and g. This is the x, this is the y. Now, from what we can understand from here is this following that if you have and okay, so what was the picture that I've showed you in the earlier slides? Let me go back to that picture again. I was saying that okay, so here the you are oscillating the uh, this this charged sheet of any metal in this direction. So what happened? It generated an electric field that was in x direction. So the generated magnetic field was in the z direction. So what you had, the propagation vector was in y direction. So that means if the question is the relationship between the electric field and magnetic fields in electromagnetic radiation is such that they are parallel to each other, they are perpendicular to each other in the same direction, independent of each other. You can see that they are not independent, obviously, because they are being generated from each other. So their directions won't be in any such kind of random directions. Okay, they are parallel. No, they are not parallel. Are they perpendicular? Yes, they are perpendicular, and the propagation direction. Uh, so we have seen that you have this s is equal to e cross b, right? This is called the pointing vector. This is called a pointing vector. So you have seen this. So where we can see that this pointing vector gives you this direction in which this electromagnetic radiation is propagating. So let's say this is E, and so if you have this E in x direction, E in z direction. Okay, so E has to be minus z direction. So E is minus z direction, then the k vector, then the s vector. This is the y cap, g cap, and this is the x cap. So then the s vector will be x cross minus g cap, x cap minus g cap, and that is nothing but z cross x cap because this will come first and this minus sign will disappear. The order itself s is equal to z cross x is y cap. So that means this will propagate along this direction. Where this electric field will oscillate along this, and the magnetic field will oscillate along this, and they had this 90-degree angle. And this is the propagation vector S cap. Okay, the propagation direction S cap, not the vector itself. And this is the B cap, and this is the B cap. Okay, so it will oscillate along this. Yes. sum it up, you will have that electromagnetic radiation. So from this, we can see that they're perpendicular. That means the quick check will be that wherever you see the electromagnetic field, you can calculate it would be and or b cos theta, and where theta is theta between E and B is 90 degrees. So EB cos 90. Okay. Now our next question is, which of the following generates electromagnetic radiation naturally? So what are the natural sources of electromagnetic radiation? So we can see that a static electric field, can it static electric field generate a radiation? So what does it mean that by static electric field? Static electric field means that, so that is del E over del T is not equal to zero. This is the time dependent electric field. But if you have del E over del T that is zero, then this is the static electric field. Now what happens when you have, okay, so try to understand this Maxwell's force equation that was that I write as del cross B is equal to 0 J plus A0 epsilon 0 del E over del T, and we understood that J vector for the source free 0, the source free, let's consider for a time being source free. So we have del cross B is equal to 0 epsilon 0 del E over del T. But if it is saying that del E over del T, its time is equal to 0 and this is constant, that is constant in function of x, y, g, but not of t. So this is constant. This implies this. And what we can do from here, that del cross B, if it is constant, so this is 0. This is 0. And from here we can see this is not the like del square B minus that means the electric field, static electric field will not generate the radiation, sunlight. Yes. So earlier I was talking about that electromagnetic radiation does not need any kind of medium to travel from one place to another. So because it's an electromagnetic radiation, so that's why this from sun to earth, the radiation comes, the electromagnetic, whatever the energy transfer comes in form of electromagnetic radiation, because they don't need any kind of medium, they just travel through the vacuum. Sun is a natural source of radiation. A charged particle at rest. So as I explained earlier, a charged particle at rest will generate an charged static electric field, because a charged particle at rest, if you consider electric field here, it generates 1 over 4 pi q over r square r cap dr. Now, if you take the del E over this time derivative, because this charge is not changing its position, it's 1 over 4 pi epsilon naught cube del, over del T r cap over r square, because they are not functions of the T. So this won't generate any static charge, will generate an static electric field. that we have seen that static electric field does not generate any radiation, electromagnetic radiation. Okay, and then a neutron. So a neutron is a neutral particle, so it has actually no charge. Proton, and neutron is charged neutral particle. So even though it's accelerated, so it does not have any charge. It has a mass, so it won't give us the electromagnetic radiation. So charged particle are the necessary criteria for generating electromagnetic radiation. So earlier we have seen that if they oscillate, if the charged particle oscillates, it generates the electromagnetic radiation. Reason being that charged particle will change the current and also it will change the spatial charge density distribution. And that changes will give you the electromagnetic radiation that we have seen in the previous equations. Okay. Now, okay, so the next option is the neutron. So that I explained. Now, which of the following is not a form of electromagnetic radiation? So what is the electromagnetic radiation first of all? That we have seen. So if it all like nearly so if you have this equation, that's del square E del x square minus del square E t square 0 c square. So that solution of this kind of thing is a physical understanding psi sorry, sine sine of x minus t. So where c is q by k, okay, c is omega by k, because omega is 2 pi mu and k is 2 pi by lambda. So this is lambda. This is the plane wave solution. But what we asked, like, which of the not is the following of electromagnetic radiation? X-rays, radio waves, sound waves, microwaves. So we can see that sound waves. Okay, so let's first start with the X-ray. X-rays are a radiation, are the part of radiation spectrum. So they also uh, are used in our daily life, like for the it can be like for X-ray. If you want to do, if you want to find out where is the bone fracture in any patient's body, you can do X-ray and you can find out the fracture there. So X-ray are the electromagnetic, strong electromagnetic radiations. They are they are they are strong electromagnetic radiation which can penetrate to our skin. But the light at the same time, it does not have that much of energy to penetrate through our skin, so it gets absorbed. And then there is this microwave. So radio waves and microwave. So radio waves, you are obviously know that's a it's a long wavelength electromagnetic radiation that is used for telecommunications and radio transmission and receiving purposes. So it is also a electromagnetic wave. And then the other one is this microwave. So in the daily life, we have started using microwave ovens in their houses, where you can see there is this microwave being fitted inside a metal cabinet, and there you put your food and it cooks the food. So that is also part of microwave, also part of electromagnetic radiation. Then the question comes like Are the sound waves or the electromagnetic radiation? The answer is no, because how the sound waves are generated are very different from how the electromagnetic radiations are. The sound waves are generated by oscillating atom, and then the next atom start to vibrate, and the vibration that you hear is uh, it's that is the vibration that you hear with your ear. But but in case of electromagnetic radiation, there is not the charge. This is not the mass that oscillates. It's the charge that oscillates and generates the electromagnetic radiation. Because that's why the neutron was not able to generate a, you can say, electromagnetic radiation. It was a neutral particle. That's why the all the vibrations that are happening in the due to this sound waves, it's not electromagnetic radiation. Because uh, it's in there, it's happening due to the vibration of the atoms, not the charged particles. And the charged particles are the criteria for this electromagnetic wave generation and other stuff. Okay. So our next question is electromagnetic wave has a wavelength of 500 nanometer. Our next question is an electromagnetic wave has wavelength of 500 nanometer. Calculate the frequency and energy of photon associated with this wave. So, okay, now I would, okay, so Einstein said that energy is associated with an electromagnetic radiation if it has frequency omega is h nu. Its frequency nu, so it's h nu, where h is it's constant. So you can see that it's Planck's constant, and Einstein is taking now talking about the energy measurement. So it's like that. But if we have this wavelength of 500 nanometer, means the lambda is 500 nanometer, then calculate the frequency and energy of photon associated with this. C is we know that is 3 into 10 to the power 8 meter per second. H we know is 6.634 into 10 to the power minus 34 joule per second. So we have this. Now we can have all this. So we can first calculate the H nu. H is before that we have to calculate the frequency. So we have seen previously that lambda nu. That means nu will be c by lambda. So he will be h c by lambda, and that h is 6.6 before 10 power 34 8 frequency. So lambda is 500 power minus 9 meter. So now it has to be in SI unit. So if you can calculate, so it will be like 6.634 power minus 34 plus 8 into 3 upon 500 power minus 9. So multiply this like this, and minus 26 about 500, 500 can be multiplied with minus 7, like 26 plus 7 5, so it will all become 10 to the power minus 18, and 5, 3 times goes 8 or something. This is the approximate. This will be like this energy associated with the photon. So I used the term photon. So what happens that this is the electromagnetic wave. So they are not the continuous, they are quantized. So electromagnetic waves are quantized. That quanta is called this lambda. So lambda. So the quanta is called the photon. So this was given by the Einstein. Told that not only the electromagnetic radiation has a transfers its energy in forms of quanta, and so that quanta is called photon. That's the term it was coined. Okay. Now, now we have to calculate this energy, and then again, we have a different question. So we have to have a traveling pulse that is given by Pxt. So let's write that down. Pxt is given as A exponential minus ax minus bt plus c. So C are positive constants. Okay, so let us go back to the slide number. So here we were asked about the velocity in this question, but before understanding that, we can understand something here. Here. So first I showed you this. Look at this diagram. So here, if you have, oh sorry, so if you oscillating with a frequency omega, and it is traveling some distance along x, and this is the uh, between these two uh, maximas called uh, if you measure the distance at the wavelength lambda. So you can write this if you are interested knowing what will have what is the amplitude of this wave at this position x. So you can write this equation as a sine omega t minus kx, where k is nothing but 2 pi by lambda, where lambda is the. So uh, this is the wavelength that this wave has, and this is the frequency that is oscillating. Now, if anyone asks, like, what is the velocity of this wave, so how it is traveling, then you can immediately see that for the velocity, this particle is doing this motion, and then going back here. So, no, it's not like that, but like this, whatever the excitation is here, it has to, when it will reach here, it will take around lambda distance. Sorry, so it is not going like this, but the excitations that are here will reach here by taking the distance lambda. But how much time then it would have been elapsed? That will be given by this frequency. So the time it take it will be one over omega, because it is the period of the oscillation. So it's like a one period of the whole oscillation. It goes up, it goes down, and then it comes back. So it goes up, goes down, and then let's say it started from here at zero. So Okay, now it's starting at maximum, right? So it started somewhere here. It goes down, then further down, then it goes here, and then it comes back here. So when the one oscillation is completed of this, some point, okay, no, I can't. But you can see, uh, but you can see, like if the particle is here, that whatever that we were oscillating with hand, its frequency omega, it is here at the top, so that correspond to this amplitude, right? The maximum, and then it goes here, and then it goes further down, so that correspond to this area, and it comes back here, and that correspond to this amplitude, and it goes back here, so it correspond to this amplitude again, maximum. Now this in whole cycle, the frequency is omega. So that means the time is nothing but 2 pi by omega. That is the time. And this is the distance it travels. The distance traveled is lambda. So if you want to calculate the velocity, the natural thing will be or how much time you have taken, how much distance you travel. So the excitation has traveled around lambda over okay lambda distance, and the time is 2 pi by omega. So we just multiply it with that, and you can get the velocity. So velocity will be v over distance over time. So distance is lambda, time is 2 pi by omega. So omega is 2 pi nu, the frequency in hertz. So you can just cancel the 2 pi, so and you can get the velocity. Okay. Okay. So now let me share my screen, and I will write it down whatever I said. So I'm saying that if you have this, let's say you have this one system as sorry, let me make it. So let's say if you have this straight line that is going up, this straight line, this straight, not straight, very straight. Now let's say this is the distance. The axis x, y. So what happens? Let's say if you have a particle, what you do? You take it to here, so it goes here. Then you take it back. So okay, so let's say the string attached to this particle. So that string will go here, and then it come back. Then so that means it will go like this, and the excitations in the string will go like this. Like you take it here. So this excitation will be like this. But when you take it back, so they will like uh, drop from here. So it goes like you draw the parallels different places. What I'm trying to say, you have this particle here performing an oscillatory motion. So it goes here. That means if you see its position, so there's state origin is zero. So it will be like this, and it goes to the maximum. Then it comes back to zero. So it comes back to zero. Then it go to maximum in the negative direction. So it goes to maximum in the negative direction. Then it comes back to zero, zero, and then goes back to the. Okay, so this is the initial position. Now these two min mass, this one and then this one. So it completes one cycle. So this is called lambda. Or you can go further if you started from here and so you come like here. So this is the maximal and it will travel the distance lambda. So this is the lambda distance it had traveled, the excitations. But the time period was t is equal to 2 pi by omega, where omega was what? Omega was this oscillation of this particle, oscillation frequency. Now, if you want to calculate the velocity of this excitation, so what you can do, the lambda, the distance, and how much time it took to excite from here to here, and then come back to here. The time was taken was 2 pi by one whole cycle, the 2 pi by omega. You have left over 2 pi, and the omega is nothing but 2 pi mu. So the velocity is 2 pi divided by 2, the velocity. Okay, so this is the lambda. Now could understand that how this velocity is calculated. But this is, so this we can see that it's a, if you write this equation, so it's like it can be written for this kind of motion as a some amplitude sine ax minus omega t. So by looking at the equation of the wave, we can tell anything about it. So even though we can tell the how much velocity the wave is traveling, what is the excitation, what is the velocity, what is the velocity of excitation. So and just by looking at it, you can take this phase phi. This is called a phase, and that is nothing but kx minus omega t. But for a plane wave, it is constant, so del phi over del t is 0, and that means that del k, sorry, del k over del x. Let's say, okay, the time derivative, so del over del t, kx minus omega t is equal to del phi over del t. But we know that this is for plane wave, this is 0. We have this del over del t, kx minus omega t. I have already told you that k is nothing but h pi by lambda. Remember this 0, k is constant, which comes out. T minus t, omega is also constant, so it also comes out del t 1, or simplified dx over dt was. So this is the displacement, this is the time, the velocity minus omega, and this is 1 multiplied by 1. So this matters. So del t over del t is 1. Then cancel out. So the velocity that is here is nothing but that's omega k. Just again substitute 2 pi mu and upon 2 pi lambda. So it's nothing but the velocity is 2 pi, sorry, lambda velocity. And this cancel it out. So lambda. Okay. Now this was for the plane. If we are asked for any given questions like here, that was in our presentation here. So what is the velocity in this question? So we have the pulse that is given by p of xt minus a of exponential a minus ax minus bt plus c. So they are saying what the speed of pulse. So, how we are going to calculate that? So it's very simple and very straightforward. That we have this p of xt is given as a of exponential minus ax minus bt plus c. We have just seen that whatever there is this uh, argument, to just take out the derivative of it, and then we can just calculate the velocity like 5 by x minus ax minus bt plus c. So del 5 del t 0, and it will be like minus of a v minus v. Del c over del t is 0. So v will be minus v by a. That means it's traveling along minus x direction. That's it. So that's why the velocity is negative. So I hope I have made it myself clear, like how you can calculate the velocity given and so it's simple that phase should remain constant, and from there we can derive all this. Okay. Uh, with this, uh, I, so with this we have like finished for the week 10. So I will record this session and I will post it on YouTube, and the links will be shared with you so you can watch them later on. And then we will meet again in the next week. And I want to acknowledge Professor Manoj from IIT Kanpur, NPTEL team, MRF team, and Department of Physics, IIT Kanpur for providing such an opportunity for conducting such doubt clearing sessions. Okay, thank you. I will see you the week at the same time from 5 to 7 every Saturday.